Morning. What we have going here today is another example of an optimization problem for Calculus 30. This time around we have a bit more of a geometry question or a problem, I should say. The scenario that they're setting up for us is that we have a rectangular piece of paper. It measures 20 by 28. Equally sized squares are to be cut out from each corner of the paper. Remaining flaps are to be folded up to make an open-topped box. Wants us to find the dimensions of the square that could be cut out to maximize the volume of the box. And so the first thing I'm going to do is I'm going to get myself a diagram going of this rectangular piece of paper. They are telling me that the paper initially is 20 by 28. And of course, because it's rectangular, those dimensions are matching on both sides. They are telling us that we are cutting out the corner, a square corner, from each of the four corners of our rectangle. And they're saying that that is going to then be folded up to make ourselves an open-topped box where we are wanting to talk about the maximum volume. So when we talk about the question itself, it says find the dimensions. That's the question. Find the dimensions of the square. That's ultimately what they're asking us to find. So when I start my let statements, again, something has to be plain old x. If that's what we're going to end up solving for, it might as well be what we're asked to find. So I'm going to let x equal the side dimension of this square that we are cutting out. So that means that this measurement is going to be x. All of these little squares in the corner are going to have that dimension, that side length of x. Now, when we talk about let statements, it's important that what we're asked to find is definitely in our let statement. But we also use our let statements as a way of getting all the pieces we need to build the equation. And because what we're asked to work with, what we're asked to maximize is the volume. Maximum volume is what I would represent my y with. But to build an equation about volume of this box, I need to recall that volume is length times width times height. And if I'm going to make an equation, I need to have expressions that represent all of those three dimensions, the length, the width, and the height. So that means I got to go back to my paper that was being folded up into this open top box. And when I think about folding these pieces, these flaps up, I'm going to have a rectangular box that is going to have this base. So this is going to be the base of my box. So what are the length, the width, and the height of that box? When I fold those flaps up, I believe that the square that was an x centimeters long is going to represent the height of the box. That piece is coming up, but I need the length and the width. And so if you take a look at our new length, it's no longer 28 because it's had pieces cut off at this end and this end. So what used to be 28 is now shorter by two x's. An x length on this side and an x length on this side has both been removed. Same thing with the width of the box. The box is no longer 20 centimeters long. This piece now is 20 centimeters, but it's lost x and x on both sides. And so we have 20 minus 2x as a width of our box. So lots of times I like to add those to my let statements. This is going to be the length of the box. 20 minus 2x is going to be the width of the box, and that x is going to be, I guess I didn't mean to put x up here. What I meant to put was the height of the box. So now that I have all my let statements, I am ready for my next step, which is to create my equation. And again, because we're asked to find the volume, I'm going to build my equation with the volume formula in mind. So when I build my equation, y equals for volume, I'm going to have my length, my width, and my height. Now, how you go about taking the derivative, whether you want to do it from this stage or expand it like I have done in the past, it is completely up to you. What I'm going to actually do with this one, I'm going to do one little step and then I'm going to find the derivative from there. I'm going to take the x and I'm going to multiply it into this one factor. And remember, when you multiply, you can only ever multiply two things together at a time. So I'm multiplying these two together and I get 20x minus 2x squared. In the previous examples, I had said you can expand this if you want. I'm going to actually leave it alone there, and I'm going to use the product rule when I go to take the derivative. So step number 3 of these optimization problems, again, is the derivative and letting the derivative equal 0. So I'm going to find the derivative, but I'm going to use the product rule. So remembering how to do the product rule. Product rule is taking the derivative of the first, leaving the second, plus leave the first, derivative of the second. So I'm going to do that. Derivative of the first is -2, leaving the second, plus leave the first, and derivative of the second is going to be 20 minus 4x. And when you take a look at letting our derivative equal to 0, we have to simplify anyway. So I mean, you can argue it would be easier to take and expand up here before we take the derivative, or I have to expand down here. I'm just showing you that you can do a variety of things and still get to the same answer. So when I expand my derivative, before I let it equal 0, I'm going to have -40x plus 4x squared. And again, we have to distribute here. So I'm going to have 560 minus now 28 times 4 is 112. X minus 40x plus 8x squared. And so my derivative looks like, when I simplified, I'm going to have 12x squared. I'm going to have -152, -192x, and plus 560 is going to be my equation. And so part of our third step is to take the derivative and let that derivative equal 0. Now we are working with a quadratic equation this time. So remember to solve a quadratic. We have two options. We can factor. We can use the quadratic formula. Those are our two most popular versions of solving it. I'm not going to worry about finding factors that multiply. I've got some rather large numbers. I could take out a common factor. I'm going to use actually the quadratic formula. So I'm just going to flip over here. And if I'm working with the equation 12x squared minus 192x plus 560, my A is 12, my B is -192, my C is 560. So using my quadratic formula, -b plus or minus b squared minus 4ac all over 2a. I'm going to end up with the negative of negative 192 plus or minus that same negative 192 squared, 4 times 12 times c all over 2 times 12. And so cleaning up my equation, my negative 192, that is going to be squared, minus 4 times 12 times 560 ends up being 9,984, and that is all over 24. Some large numbers. I guess if I would have divided my equation out, I might have had some smaller numbers, but we can continue here. Square root of that 9,984 is 99.92, and we can take a look at our two solutions. So we're going to have 192 plus the 99.92 all over 24, and we're going to have the 192 minus 99.92 over 24. So the two solutions that we end up with, 192 plus 99.92, and make sure that you finish the top before you divide by 24. And these calculators, they like to follow strict order of operations. So the first solution I get is 12.16, and the second solution that I end up with is 192 take away 99.92 divided by 24. And I get 3.84 as the other solution. And so when you take a look at these two solutions, if you go back to the fact that we had a rectangle that was 28 by 20, x represented the square that was going to cut out of the corner. So are we cutting out 12.16 centimeters from every corner? Are we cutting out 3.84 centimeters from every corner? Well, the 12.16 would be a little bit difficult, because if I cut out 12 centimeters from this side and another 12 centimeters from this side, we wouldn't have anything left of our width. So this one does not make sense logically, whereas the 3.84 would be possible to cut out the corner from the square. So that means that we've reasoned through what is a reasonable answer for our scenario. And going back to the original question that wanted to find the dimensions of the square. And so the square to be cut out would be approximately 3.84 centimeters by 3.84 centimeters. And again, understanding that this is the x value of this maximum volume. If I were to find the corresponding y value, that would represent the volume. This is the x value that represents the square. And so we could have more information if we were to go back to our equation. But the question, again, specifically want to know about the square and what size it would need to be to maximize our volume. So there's another an optimization problem for Calculus 30.